Okay. So let's look at part A, because part B, we have to figure out how to get that formula. I just want to give you one to work on your own, totally, with a little bit of structure to it. So here, obviously, x bar is 8.4, standard deviation is 2.5, n is 37, and then 95% confidence, we just did that, 1.96. So you start to see these numbers over and over. The most used confidence interval is the 95% confidence interval. So you normally use that 1.96 number. Well, 1.645 comes up a lot, 2.33 comes up a lot, 2.575 comes up a lot. So here Z is 1.96. So I got everything I need then to construct my confidence interval. So we throw this stuff in here. Yeah. Yeah.
Is it 0.0?
Standard deviation?
Oh.
0.25, right? 2.5?
I thought you were doing
No, sorry.
Oh, never mind.
That's right. And then when you do the error, what do you guys get for that?
0.87.
0.8.
0.80555.
All right, so 806 or 0.81 even. That's good. Yeah, I'm going to use 0.81. Chalk. So it's not a bad idea to go out 1 decimal further than this is. You don't have to go much more than that because you only have to be at least as certain as this thing is. So then you just add and subtract that. So you say we're going for minus 0.81. 59.
Yes.
And then add it, so it'd be 69.21. So that's your quick little, there's the interval. And now you write the conclusion that includes the units. Okay? So we are 95% confident. That what? No, be careful. The order we say this matters. The mean is somewhere. It's our interval that could be in different places. So we are 95% confident that this interval contains the true mean, not that the true mean falls in this interval. Believe it or not, it's semantics, I know, but it's totally wrong the other way. The mean doesn't fall somewhere. The mean is just sitting there waiting to be discovered. Our interval is the one that could change depending on who we picked for our sample. So we are 95% confident that this interval, that the interval 67.59 inches to 69.21 inches contains true mean height of mid. I didn't say what area or whatever. It's a very boring movie. True mean height of mid. All right, I like it. So be sure to include the units. Don't make me be a dorkier person than I actually already am and have to say yards and sort of shit. All right, I like it. So that part's nice. Now let's investigate what the next question might reference. And the next question is really related to the idea of feasibility. How feasible is it to be within a certain amount? So this part B is really getting down to the point where if you want to be within a certain amount, how large of a sample would it take to get me there? So here, with a sample of 37, I got to within 0.81. So this part B is saying, well, what if I wanted that to be 0.5? I want to be within half an inch. How big of a sample would I need then? So obviously it's going to have to be how related to 37? It's going to have to be bigger or smaller? Bigger, because I want to be more sure about my mean in the first place. You guys get that? To make my error smaller, I make my sample bigger. This question is really just how freaking big does it have to be? So let's look at what affects the sample size. This part, of course, was the error, right? So I'm going to say the error is this. So now comes the little bit of algebra. Can you solve that for n? Well, yeah, because you can see the answer up there. But how the hell did I do it? How do I solve this for n? And you're like, I thought that was behind me. No, it's the whole reason you took those classes, because they actually work in the real world. Algebra. Poor little algebra. How do we solve this for n? What sucks about n? Two things. It's a square root on it, and even worse, it's on the freaking bottom. So I can actually do this. It's one of the most important little things to learn from algebra is I can multiply by that and divide by that shit. So these just switch places. Watch this. 10 is 20 divided by 2. Is that true? So then 2 is 20 divided by 10. I just switch places and it's still true, of course, because they're both parts of 20. So I can switch square root of n equals z sigma over e, and then how do I kill the square root? Square. So that's where that formula comes from. I think I wrote it with a square next to everybody, or did I? Yeah. You can either have it like that, or you can have a square next to everybody, however you like better. So this, if I want a certain error, and a key word for error normally, but not always, is within. Because that's how much I want to be within so much. That's the error I want to allow. So they tell me what error I want, and then I can figure out what the sample size. So if I put 0.81 in here with all this other shit that I know, I'm going to end up with n equal to 37. Because we already know that 37 sample size leads to 0.81 error. You guys get the idea here? I want to know what sample size leads to 0.5 inch error. Right? So what's my z-score again? 1.96. Standard deviation was 2.5. Divided by the error. And I want to make it what now? I love you guys so much. I don't want to make it 0.81 because I already know that 0.81 goes with 37. That's not much of a question because we already know that. I want to force it to be what on part B? 0.5. I want to force the error to be only 0.5. And I'm asking how large of a sample is. If it's 100, maybe I could do that. If it's 8,000, that might be beyond me. That's why it's a feasibility study. How feasible is it to accomplish that? This will be 0.5. Roughly 100, actually, yeah. Very roughly, it's like 98. So you're 96.04? You always round it up because it's really hard to get 0.04 per person. So if I want to be within 0.5 inches, I don't round that down to 96. I have to round it up to 97, so it's even better. I can't get the 0.04 person, thank God. That person is going to freak me out. So we round it up to 97. How many people did we already talk to? 36. How many people would more would I need? 60. Yes, right, 97 minus 37, 60. So I could talk to 60 more people, that seems pretty feasible. If it took 1 million people, maybe not. Maybe that's a little not feasible. I'm like, boss, you gotta step off. Can't get that close, can't do it. Maybe. So try to do part B there on this page. Oh, you already did part B. Forgot, I thought I was doing the example. So I mean, most of the time it's going to be the word within. They might say something like we want to be off by as much as, or we want, but most of the time it's going to have to be that word within. That's what tells you what to put in place of E. That's what you want to force the error to be. I always get people that put that error in. But of course your answer is going to come out to be this, because we already know that. We already know that that sample size leads to this error. I want to know what sample size leads to some other error. Okay, maybe. So here, what if I wanted to be within 1/10 of an inch? What would the sample size be then? It would be
2,000.
yeah, it would be what now?
2401.
Yeah. 24, so it's like 2,400 something, and
01.
then you round it up to 2,401.
That's exact.
Is exactly?
Yeah.
That's freaking me out a little bit. Yeah. So it seems weird, doesn't it? Just to be 0.4 inches closer to the real mean height, you got to get in the thousands, 2,000s, right? 2,400 people. That's crazy. But yeah, of course that's what it's going to take to get that much closer to the real mean, is to get the error down to that much. I want to get it 1/5 as much as it used to be. So this is a feasibility study. Maybe that's not feasible for us, so we just got to go, well, I can't get to that. I can't do it. There's too many people for me to talk to. Okay, maybe. So go ahead and do part C. You should be able to answer the first part of that question without doing any work.
Pretty large.
So just to help you out a little bit, if I want to be 95% confident, and I don't like fish. I kind of like fishing, but I don't like fish. So I'll catch it and give it to somebody else. Here, enjoy that. But the thing that came to mind when I first learned this was like a fishing net. So if I want to be 95% sure that I catch a certain fish, I got to throw out a net, this big. I got to catch 95% of all the fish to make sure I caught this one fish. Are you guys kind of with me? To be 95% sure that I caught the actual fish, I got to catch 95% of the fish. Well, there's only a 5% chance the one I wanted got away. The one that swallowed my engagement ring or whatever, right? You guys with me? So if I want to be 90% confident, I only have to catch 90% of the fish. So now my interval can get smaller. It only has to catch 90% of the data. The z-score is going to get smaller, right? For 90% confidence interval, it's going to be a smaller z-score. You can see the more confident you want to be, the larger your interval has to get, because you have to catch that much more to be that confident. Less confident, you can go out less far. So now if you actually do the work, you should see that your interval is not as wide as it was in part A. So do the work for part C. So we did 90% before. Remember that was the one. What was the z-score for that?
1.645.
Yeah, 1.645. So we have, this is the same problem, same sample mean as before, 68.4. Give or take 1.645 of these. Let's see, and the n was still 37. Yeah. 0.68? I like it. So then it's from
67.72 to 69.08.
I like it.
Yeah, I did that the first time.
What? Oh, this one? Oh, okay. So you've been sitting on that for a while. Okay. And what was the interval we got for part A? I remember, who's got
Part
that?
A was 67.59 to 69.21.
21? So that is narrower than this. People sometimes miss that because they say, that's bigger than that. What do you know? It's narrower, right? The error is less. Which makes sense because we're allowing ourselves to be less confident. So we don't have to catch as much of the data. So 95% is sort of that middle ground where you catch enough of it to be decently sure, but if you try to be 99% confident, you start to get really huge intervals, and it's not very useful. Now, just to show you a couple places in the real world where this is used, I found a study. Very often studies are pretty morbid, but this one's still kind of morbid because it's not about death, but it's about fried potato consumption, association with elevated mortality. Have you ever watched, what's it called, Sling Blade, the one with Billy Bob Thornton? No? You guys have never seen that movie? Oh, guys, all right. Too bad. He likes fried potatoes. I'm all right person for fried potatoes. Look right here. This should look very familiar. Right there. 95% confidence interval. So people that just ate potatoes did not show an increased risk of overall mortality. So I guess a 1 would be normal amount of mortality, of death, right? Whereas if you ate fried potatoes 2 to 3 times a week, the 95% confidence interval does not include 1 anymore. Do you see that? The 95% confidence interval goes from 1.11 to 3.41. If 1 is the normal amount of death, that doesn't include 1. That's an elevated risk of death. 95% confidence interval is the most used confidence interval. I like it. So a lot of times, now what took me a little while was the way I find these kind of things really quick is I go to Google and I type in study, and then I restrict to, like, I went to the past month. I had to go to the past year to find a decent one. We had some really freaky ones, but just type the word study and then search for the past month or the past year, and you get some interesting studies that have been done. And then if I can find the link to the journal article, that's where I can really see the confidence interval stuff. If I just get a magazine article, it's going to talk about the surface shit. I want to get to the real data, right? So I got to find the article. Took me a little while, but I found a nice one. Okay, just to let you know that the stuff we're doing right now is immediately applicable to stuff that people are doing and being published in journal articles and showing evidence of whatever. Yes, 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 okay. All right, so last thing for today. Last thing. Yeah, the other side. And notice how I skip A2. In fact, I don't know if you guys have noticed on your homework sheet, I go 8-1, 8-3, 8-2. And the reason I do that is because 8-1 and 8-3 both use z-scores, the normal distribution. 8-2 uses something else, because 8-2 is where we're like, all right, we don't even know freaking sigma. So things have got to change a little bit for section 8-2. That's why I skipped that and come back to it. This is the last thing for today, so just hang on. You'll be right. I can sense people like, oh my God. All right. So remember how we developed the formula for 8-1. We started with this, basically, right? So I want to develop a formula that will create confidence intervals related to like the political stuff I was talking about earlier. I want to make confidence intervals for percentages, not for averages. I want to make them for percentages. So then I can say 44% are going to vote for proposition whatever, plus or minus 4%. That's going to be the error that we can calculate, right? So I start with this again. Now somebody help me. Did we replace this with x bar, right? Okay. And let's see. For binomial, because when I start dealing with percentages, either you're going to vote for it or you're not. So it's a binomial situation. Whatever the percentage I'm talking about currently, there's an opposite situation, right? So it's going to be a binomial situation. What was the mean
For what?
for binomial? NP. I like it. Now, you're going to love this. See how I use a population symbol here? Because that's normally the P had to be for a whole population. 11% of Americans are left-handed. Okay, that's a population. Now, what am I going to do here, though? I'm going to be taking samples, right? You're going to love this shit. You ready? Oh, you're so ready. You know how mu is a symbol for population mean. X bar is for sample mean. There's got to be something related to a sample percentage. So you see how the X gets to wear a little bar? So now my P gets to wear a little hat. And that is actually the name of that. It's the P hat, the thing you don't want to wear. So it's, yeah, come on. No matter what clothing is wearing, though, P hat and Q hat still have to make one, right? You guys with me still a little bit? So the only difference between these two is this percentage is from a sample, not from a population. All right. And remind me, so what was the sigma before? What was sigma for a binomial? NPQ. So now S is going to be NP hat, Q hat, sort of, right? Sort of S. Let's just say sort of S. All right. So let's replace what we know. So I sort of did this already. Now let's replace. This is going to be NP hat, give or take. Now this is just the derivation of the formula. Don't freak out. This is not going to be involved with your work. This is where the formula comes from. Right? Crazy Jeff wants to do this always. Give or take Z, and then sigma I'm going to replace with the best approximation, square root of NP hat, Q hat. And what is this trying to get a hold of? What is this trying to get a feel for? It's trying to get a feel for the mean. Right? So is that decent if I write it like this? Is that right? The mean is approximated by this. Is that cool? And of course, what's the mean in terms of NPQ? It's NP. NP is approximated by this. Stay with me now. This is getting freaky. So again, I started the same place we did before, but now I want to put the binomial shit in there to create percentage. And what's wrong with this? Is this an interval for a percentage? No, it's still a freaking mean here. So what do I need to get rid of so it's just a percentage there? You need to get rid of n, right? I don't want to approximate NP. I want to figure out where the percentage, where's the population percentage at? So if I divide everything by n, the percentage, the population percentage, is estimated by my sample percentage, give or take, this shit. Now, there is something I can do with this shit here, a little something. Can I kill the ends?
Yeah.
You so wish you could. Why can you not?
I think it's
This is a whole n. This is half of an n, right? N to the 1/2, square root of n. So you can't do that unless they're the same root. So n is also the square root of n squared. Then you've made them have the same root, right? You guys see that? Square root of n squared is n. So, ooh, Jeff, it's amazing what you just did. But what I just did was allow myself to reduce this shit. So you get plus or minus z, square root, b hat, q hat over n. you guys so much. So again, we started same place. We replaced it with binomial kind of stuff, specific stuff, right? What the mean is in the binomial, what the standard deviation is in the binomial. And then the one thing that's a little bit weird that I have to introduce this guy over here for is to get rid of the stupid n's. I have to divide by n everywhere. So this is if I ask you to find a confidence interval for the true percentage of people that will vote for this, or the true percentage of people that smoke marijuana, or the true percentage of whatever, right? You're going to use this formula to do it. So for example, let's do one example. So this is now a formula. So if I say find the confidence interval for the true percentage, you're going to use this dude, right? So let's say this from a sample of 802 people. We find 512 want to legalize marijuana. Right. What is the true percentage of people that want to legalize marijuana based off of this study? Find the 98% confidence interval for true percentage want to legalize marijuana. So what we need for the formula is we need p hat, q hat, z, and n. Well, n, we got staring us in the face. Hopefully you picked the right number. What's n? 802. The total number of people. What's p hat? What's the percentage I see in my sample?
512 divided by 8.
Beautiful. 512 out of 802. The number of successes divided by n. 512 divided by 802.
0.638.
0.638. Hello? Yeah. And I love the fact that you went out 3 places. Always go out at least 3 places with p hat and q hat. So if you want to, if you go out 4 places for every damn thing, you're golden. Do you guys
Not in my physics class.
say it?
Not in my physics
No. I don't care what I'm talking about in my class. Your physics people can do whatever the shit they want to, right? Here, if you go out 4, you're covered for everything. Do you understand what I'm saying? If you forget, you're like, what is it? You go out 4, you're fine. You're covered. Second?
Decimal places.
Yeah, so
Oh,
p hat, q hat go at least 3 decimal places. So if you go 4, you're fine. Okay. What's q hat got to be then?
0.362.
Yeah, it's got to be the opposite of this. It's got to be 1 minus this, right? 0.362. I like it. And what's the z-score going to be? We did that one earlier. Who remembers the 98% z-score? Did we do that one earlier? Or am I? Yeah, 2.33. Z is 2.33. Bless you. So we got everything we need for the formula. You take away all this derivation business. So I got p hat, 0.638, give or take, z, 2.33, square root of 0.638 times 0.362 divided by 802. Now the mistake people make, if you got one of the newer calculators, most of you guys should have one of those where the square root side just gets bigger. You can see that it's under the square root. If you have the old one where it opens a parenthesis for you, you do not want to close it until you got all the shit in there. If you close it, you're outside of the square root. It's not going to come out right. Garbage in, garbage out. So try to figure out what the error is. Don't say anything yet. Try to figure out what that error is. I love it. Raymond's like, let me see it. All right, what do you guys get for the error? Go ahead.
0.0395.
All right. So I get 0.0395. It's like 4%, right? See it?
7? No, on the board.
95.
Plus or minus.
Plus or minus. Yeah, plus or minus. So 0.638, give or take, 0.0395. So it's at the bottom of the screen. So they say on the news they'd say from a recent study, 64% of Americans would like to legalize marijuana. At the bottom it'd say plus or minus 4%. Right? So how do you make this get smaller? Well, you can take a larger sample size. You can actually make your confidence interval less, which is sort of underhanded a bit, to be honest. We're a little less confident making it look better. No, it's no good. So then you just have to do like we did before, subtract this and add it. I don't know. What do you guys do?
595.
3. Yeah, 5,985 up to
6775.
6775. Sounds all right. So then you can say, just like we did before, you can say the conclusion. We are 98% confident at the interval what?
Percent.
Yeah, good. 59.85%. My percent is acting like my units now. 59.85% to 67.75% of, it's kind of implied here, but of Americans want to, at the interval, no, get out of here, Jeff. Contains a true percentage of Americans. I like it, of Americans that want to legalize pot. Let's make a smaller word. Put it into your burrito, for example. So it feels very similar. The creation of it is very similar to the creation of the other confidence interval. And this is the kind of thing you can see in these journal articles immediately, is these confidence intervals. All right, so I think that's plenty. There's still some stuff to fill in for Section 8.3. So next time we'll do Section 8.3, we'll finish it, and then we'll get into Section 8.2, see what the hell's going on with that. Yeah. Oh, cool.
Can I get an extra one of those? Or
Yep.
Kyle?
Thank you.
Is there meatballs left in here? They have a taste.
So I didn't see it.
It might be.
Normally if the teacher sees it, they would put it up here. Somebody has sold it. Make sure you get your, you give me back my calculator. Get your ID back. If you borrowed a calculator. I think. Yeah. Sweet. Thank you. Sure. Oh yeah, I know. As soon as I get a makeup made, I'll let you know.
Okay.
Yeah.
Yeah.
Please. Yeah, tomorrow's Thursday, so from 8:30 to 9, from 12 to 12:30.
Sorry.
Where else are you? Places? Oh, yeah. Cool. Thank you.